Hi, this is Group 22, and for our technical presentation, we decided to focus on statistical engineering seismology. To start off with a brief explanation of earthquakes, an earthquake is an extreme and violent shaking of the Earth's surface by the plates along the cracks grinding together, causing pressure to the point of rupture. In a seismic period, the Earth's plates move relative to each other except at most plate boundaries where they are locked. Reed's theory states that the more the rocks are strained, the more elastic energy is stored and the more significant potential for an event. And the image shows a convergent boundary. The elastic rebound theory is an explanation for how energy is spread during earthquakes. A sudden movement occurs along the fault, releasing the accumulated energy, and the rocks snap back to their original shape. This theory was the first to significantly explain earthquakes, as previously it was thought that surface ruptures were the result of strong ground shaking. So how is the intensity and magnitude of an earthquake measured? For magnitude, we can use the Richter scale, which is a mathematical equation used in seismographs to calculate an earthquake's magnitude by the force or energy. For intensity, we can use the modified Mercalli scale ranging from 1 to 12, which measures the intensity of the earthquake, which is the destructive power of the earthquake. So how do statistics play a role in predicting earthquakes? With the use of statistical models, the Weibull model is a tool that can be used to model the effects of earthquakes on buildings, machines, and products over time, and to estimate the probability and magnitude of earthquakes. And the image shows the earthquake recurrence law in the Weibull distribution. Next, we will be looking at the types of waves. P or compressional waves are the first to arrive, so they're the fastest seismic wave. They can move through all forms of matter and they leave behind compressions as they move through. Rayleigh waves are the waves that you'll be feeling most of the shaking from. The motion is the opposite of an ocean wave, and they roll. S-body waves are the second waves to hit the seismograph. Shear waves can only move through solids shaking the medium perpendicular to where they are traveling. The image shows the SP interval seismograph. Another statistical model is the Poisson, which estimates the probability of earthquakes by using the complement rule, which requires independent events, homogeneity, and constant probability. Types of predicting tools. Seismometers detect and measure earthquakes by converting vibrations due to seismic waves to electrical signals, which are used to determine where and how big an earthquake is. How do engineers use statistical seismology to build earthquake-safe buildings? Engineers use earthquake data to help build buildings that will withstand the potential earthquake forces. By knowing the potential power of earthquakes in a location, engineers can decide which materials and building methods will work best. One of the main seismic safety features in buildings lies in their flexible foundation. Using a method called base isolation, engineers construct buildings on top of flexible platforms made of rubber, lead, steel, or wood to lift the foundation above the earth. So when an earthquake hits, the isolators vibrate, allowing the structure to absorb the waves and steady the building. And the image shows the equipment stud on top of the top plate, which is on top of the molded rubber or the flexible element. It also shows the concrete stud and base plate on top of the foundation. How do engineers use statistical seismology to build earthquake-safe buildings? Trusses are another major seismic safety feature commonly used in large, tall buildings. Shear walls add rigidity to a structure. These walls limit creative designs but play a crucial role in earthquake protection. And the image shows shear walls. And to conclude this presentation, these are the references. Thank you.